Okay, so we just constructed the Purina fractal using an iterative process, and I hope that you were able to see the similarities between the construction of the Purina fractal and the construction that you found for the Sierpinski carpet. And so with both of them, you're starting with a solid square and removing some in the next stage, or you can also think shrinking down and duplicating that square some number of times in the next stage. So what I want to do next is talk you through, I know there have been a lot of examples here, but I feel like you start to see a little bit more of the patterns better by looking at a lot of different types of examples. So what I'd like to do next is to walk you through the Koch-Snowflake construction for this curve here. And I'll say just briefly how that curve is similar to this particular construction of the Loxo space below. And we'll actually do some computations with geometric series and the Koch curve. So I won't talk as much about the other pictured fractals, but I want to be working in particular with the mathematics behind the analysis of the Koch curve. So let's talk about this curve. Unfortunately, I didn't leave enough space for me to really work through the construction fully, very carefully here. So I'll have to do a little bit of scrolling back and forth here. So I'm going to go ahead and move down here, and we'll come back up and look at the picture as needed. So, and you'll have it in front of you on your printed notes. So, okay, so here, if we're thinking about the Koch-Snowflake curve, the construction for this is iterative, and in fact, I'm only going to here do the construction for a single side. Okay, and by that, I mean just this yellow circled part. We'll see how to construct one side, and then you can see that in fact, if I glue together 3 of those, then we would get the full curve. So, all right, let's go ahead and do that. So the first stage of this construction is, so stage 0, we'll start counting at 0, is just going to be a line segment. Okay, and then stage 1, well, we're going to remove the middle third of this line segment. So I'm going to just go ahead and mark there, and in stage 1 we will keep the outer edges. So let me go ahead and that here, and then we will add 2 more line segments as I've drawn here. So initially, the length of the segment is 1 in stage 0, and we've divided these into equal pieces, so each is length 1/3. And now in stage 1, we kept those outer segments, length 1/3, and the segments we've added are length 1/3 too. So let me just point out here that if you were thinking about this triangle here that's made, that's an equilateral triangle. Okay, this orange is not part of the fractal, it's just the blue line segments here. Okay, and again here, this length is still 1. So now in stage 2, you can imagine what's going to happen here. All right, I'm going to go ahead and erase these highlighted bits. So what we're going to do is apply the same procedure that we used to get from stage 0 to stage 1. We're going to use to go from stage 1 to stage 2. And so in particular, what we're going to do is we'll take each of the 4 smaller line segments and we'll do the same operation to those. So what we'll do is we will take this first line segment, we'll chop it into thirds. We'll do the same with the other line segments. And then in the next stage, what we'll have will be, we will delete that middle third of each of those. And we will add in two line segments of equal length there. So each of the line segments here will be length. So there are now 4 line segments here. Let me go ahead and erase these. This didn't come through very clearly. So each of these 4 line segments has length 1/9 now. So the original line segment from here all the way to here, going straight through, would have been 1/3, and we've split that into thirds, so we have 1/9. And again, the total length from one end of stage 2 to the other end of stage 2 is still 1. So if we were to try to go to stage 3, you could imagine what does end up happening. Before I do that, let me just comment that another way to think about this is to shrink down the stage 1 picture to 1/3 of its size, and then glue together 4 stage 1 pictures. And so there's your 2 ways of thinking about this construction. And then I'm not going to go ahead and draw the next one. I'll just put ... We continue in this fashion. And let me go ahead and just scroll back up here, and you can kind of see how that's happened here, right? So, well, why not? Let's do stage 3. And then we'll put the ... Okay, so in particular, we're going to have, let me go ahead and zoom more, right? And now I'm right here in the construction, and then we can come up here, and let's see, let me go this way. Okay, and now I'm up here, and oops. Okay, and I'm adding one here. Let's see. All right, so this is the problem with drawing these things. That it's possible to not quite get back to where you started if you didn't do it exactly. But if you have your computer here to help you out, this is usually a lot easier to get in scale here. So we'll just oops. I'll just finish this up here. Okay, so there's the stage 3 diagram here, and you can see that I've replaced every one of these segments in stage 2. I've replaced with a corresponding sequence of or set of 4 smaller line segments in stage 3. And so here, each tiny segment has length 1/27th, right? So 1/3 of the length of the previous one. And you can start to see that this is getting really fuzzy looking, and it's kind of having this snowflake look. As I zoom out here, you can see that it's having the same look as what you get in the limit. And so now you just continue ... Okay, so let me just briefly kind of point out how this is similar to the Loxo space. And here, so the Loxo space actually contains lots of little copies of this snowflake curve where the angles are, they're getting a little bit distorted here, but let me just show you some of these little copies here. So if you just take every time you see a branch, you go up, right? Then what you end up seeing there is going to be looking like a copy of the snowflake curve. So the Loxo space here is actually, it has lots of little copies of snowflake curves in it. It's kind of beautiful, but then in the Loxo space, there are also these paths that go down instead of just always up. So you can see here that you've deleted the center. If you started with just a line going straight through, let me do it with another color. If I start with just a line going through this space, and so my first stage was a green line, right? Then in the second stage, we'll try this in blue, right? I could delete the middle portion here, and I would have something like a stage 1 from the Koch curve. And then if I switch colors again, right, each part of this blue line I could delete and substitute in some more pieces, and I would end up with what looks like stage 2 of the Koch curve. All right, so you can kind of see how the Loxo space has many, many copies of the snowflake curve embedded in it. And so it's actually a very interesting space for a lot of reasons, and has been used for a lot of examples in a field of study called where you work with objects called metric spaces. So there's a relationship there. What I want to do now is go through carefully the construction of the calculations for the length and the area inside this snowflake curve. And so the first thing I just want to point out is we constructed the just one side of the snowflake curve. So we would glue 3 of these together, and then what we'll do is we'll compute the area inside, and we'll also compute the overall length of the curve. So in order to keep these files a little bit smaller, I'm going to go ahead and stop the video here, and when we pick up, we'll do those 2 computations.